Welcome dear learners. We are continuing Unit 4 Fundamentals of Analytical Chemistry. In the present module, we are discussing iodometry and iodimetry. The contents of this module are iodine as an oxidizing agent, iodimetry and iodometry, starch indicator, selected examples belongs to iodimetry and iodometry, equivalent weight calculations and problems based on these concepts. First of all, iodine as an oxidizing agent. You are familiar with the element iodine. It is a halogen. It belongs to the halogen family, that is, the halogen family members you are familiar. They are fluorine, chlorine, bromine, iodine, astatine and tennessine. So, iodine is the fourth halogen. Iodine can act as an oxidizing agent. Iodine, abbreviated as I2, can act as an oxidizing agent in redox reactions, meaning that it gains electrons and is reduced in the process while causing other species to be oxidized. You are familiar with a redox reaction. A redox reaction is a chemical reaction where oxidation and reduction occurs simultaneously. Iodine can act as an oxidizing agent and that oxidizing agent undergo reduction. At the same time, the next reagent will undergo oxidation. Iodine acts as a moderate oxidizing agent. You are familiar with highly powerful oxidizing agents like concentrated nitric acid, acidified potassium permanganate, acidified potassium dichromate, etc. But iodine is not powerful up to that strong oxidizing agents, or we can simply say that iodine is a moderate oxidizing agent. Iodine acts as an oxidizing agent and it is reduced to iodide ions in its reaction. That is, in the case of iodide ion, the oxidation state is -1. So, when iodine acts as an oxidizing agent, it gets reduced to I-. That is, I2 plus 2 electrons produces 2I-. In the left hand side, iodine I2 is present in zero oxidation state, whereas in right hand side, I2 is just converted to I- ion where its oxidation state is -1. The oxidizing power of iodine lies between that of bromine and chlorine. So, iodine is a moderate oxidizing agent. Now, we can have an outlook on various reactions where iodine acts as an oxidizing agent. This is the first reaction, that is reaction of iodine with thiosulfate. Thiosulfate ion is having the molecular formula S2O3 2-. We can have this reaction. Iodine plus 2S2O3 2- gives 2I- and S4O6 2-. That is, during the course of this reaction, iodine is reduced to I- or iodide. At the same time, the thiosulfate ion, that is S2O3 2-, is oxidized to tetrathionate. Tetrathionate is S4O6 2-. We can take a typical example for this reaction, and the typical example involves the oxidation of sodium thiosulfate with iodine. And during the course of this reaction, iodine is converted to sodium iodide. At the same time, sodium thiosulfate is converted to sodium tetrathionate with the molecular formula Na2S4O6. Moving on to another reaction which shows the oxidizing capability of iodine. This is nothing but reaction of iodine with the sulfite, that is SO3 2-. This is the reaction. I2 plus SO3 2- plus water produces 2I- plus SO4 2- and 2S plus ions. In this reaction, it is very well clear that Iodine is reduced to I minus or iodide. Sulfite, that is SO3 2 minus, is oxidized to SO4 2 minus, that is nothing but sulfate. That is, sulfite is oxidized by iodine to sulfate. This is a typical example. Na2S2O3 plus iodine plus water produces Na2SO4 plus 2Hi. Moving on to next reaction, that is nothing but reaction with arsenite. That is, we are considering reaction of iodine with the arsenite. Arsenite is ASO3 3 minus. This is the reaction. I2 plus ASO3 3 minus plus water produces 2I minus plus ASO4 3 minus plus 2H plus. As in the previous case, in this reaction also, iodine is reduced to iodide and arsenite, that is arsenium 3 plus, is oxidized to arsenate, that is where arsenium is present as As plus 5. This is a typical example showing this reaction. Na3ASO3 plus iodine plus water gives Na3ASO4 plus 2Hi. That is, arsenite is oxidized to arsenate. In the typical example, sodium arsenite is oxidized to sodium arsenate. This is the fourth example where iodine acts as an oxidizing agent. That is, reaction of iodine with iron 2 plus, that is Fe2 plus ion or ferrous ion. This is the reaction. I2 plus 2Fe2 plus gives 2I minus plus 2Fe3 plus. In this reaction, it is very well clear that iodine oxidizes Fe2 plus to Fe3 plus. That is, it is very well clear that ferrous ions are oxidized to ferric ions by iodine. This is a classical example for redox titration in analytical chemistry. That is, you can use iodine as an oxidizing agent for the conversion of ferrous ion to ferric ion. Now, this is another example where iodine acts as an oxidizing agent. This is the reaction of iodine with tin 2 chloride, SnCl2. In tin 2 chloride, tin is present as Sn2 plus. This is the reaction between iodine and Sn2 plus. It is clear that iodine reacts with Sn2 plus and converted to I minus. At the same time, Sn2 plus is oxidized to Sn4 plus. That is, Sn4 plus is produced as a result of oxidation of Sn2 plus by iodine. Now we are discussing about iodimetry and iodometry. In general, we are studying about volumetric analysis. In volumetric analysis, we are measuring the volume of a known substance to find out the unknown concentration of other substance or the analyte. We can have several titrations or volumetric reactions based on iodine. The general category of all reactions involving all volumetric titrations involving iodine belongs to iodimetry or iodometry. Now we can have more details about iodimetry and iodometry. The volumetric analysis based on the use of iodine as an oxidizing agent is called iodimetry or iodometry. Here there are two terms and we are now going to clearly differentiate the two terms iodimetry and iodometry. First of all, we are discussing about iodimetry. Iodimetry deals with direct titrations involving usage of iodine solution or using of iodine solution. That means the volumetric analysis where we are taking direct titrations involving iodine solution, that is considered as iodimetry. However, in the second category, that is nothing but iodometry. Iodometry is different from iodimetry. This is the difference. Iodometry deals with the titration of iodine liberated in chemical reactions. So, in the first case, that is iodimetry, we are using direct iodine solution for a titration. However, in the second case, that is iodometry, liberated iodine is used for the titration. There are so many chemical reactions in which iodine is liberated quantitatively, and that liberated iodine can be used for the titration. This is the difference between iodometry and iodometry. Now, some examples for iodometry are here. The concentration of given iodine solution can be calculated by direct titration with the standardized sodium thiosulfate solution. This is the equation responsible for that titration. 2Na2S2O3 plus iodine, you are getting Na2S4O6 plus sodium iodide. This reaction is also familiar to you. This is because iodine acts as an oxidizing agent here, and it just converts sodium thiosulfate to sodium tetrathionate. At the same time, iodine is get reduced to sodium iodide. Now, iodine oxidize the solution of sodium thiosulfate to sodium tetrathionate. Now, examples for iodometric reactions. Reagents like copper sulfate, KiO3 or potassium iodate, K2Cr2O7 or potassium dichromate, etc. can liberate iodine from potassium iodide under suitable conditions. This simply implies that it is possible to liberate iodine from potassium iodide by using these set of reagents or these kind of reagents, but the conditions may be different. We can enter into some examples. These are examples. Copper sulfate plus 2 potassium iodide, you are getting CuI2 plus K2SO4. CuI2, 2 molecules of CuI2 just converted to Cu2I2 and iodine gas is liberated. So, it is very well clear from these two steps that copper sulfate can liberate iodine from potassium iodide. Similarly, potassium iodate or KiO3 can also liberate iodine from potassium iodide as per this reaction. KiO3 plus 5 Ki plus 6 molecules of HCl, you are getting 6 KCl plus 3 iodine plus 3 molecules of water. Similarly, it is also possible to liberate iodine from potassium iodide using potassium dichromate. This is the reaction responsible for the liberation of iodine. K2Cr2O7 plus 6Ki plus 14 HCl molecules, you are getting 2CrCl3 plus 8 KCl plus 7 water plus 3 molecules of iodine. That is, it is very well clear that the reagents like copper sulfate, potassium iodate, potassium dichromate, etc. can liberate iodine from potassium iodide. It is possible to use these liberated iodine in volumetric analysis or volumetric titrations. So, these all are good examples for some iodometry reactions. Iodine liberated in the previous reactions are quantitatively liberated, and during these reactions the quantitatively liberated iodine can be used for estimation or titration or in volumetric analysis. The liberated iodine can be titrated with a standard solution, for example, a standard solution of sodium thiosulfate to estimate these materials. Now, in iodometry and iodometry, we must have an indicator. The most suitable indicator whenever we are discussing about the titrations involving iodine is nothing but the starch indicator. Now, we can enter into details of the starch indicator. Starch acts as an indicator in iodine based titrations. That means in iodometry or iodometry, you can use starch as the indicator. Starch reacts with iodine in the presence of iodide ion to form an intensely colored blue complex, which is visible at very low concentrations of iodine. That means even very traces of iodine can be indicated by the blue coloration of the starch indicator. The blue-black color disappears when iodine is consumed or reduced to iodide ion or I- ion. That means starch will show a blue-black coloration only in the presence of I2. If all the I2 converted to I- ion or it is removed from the medium, then the color will disappear. The indicator is added near the end point or near to the end of the titration when the color of the iodine solution fades to pale yellow. Generally, in order to avoid some errors, we are generally adding starch indicator nearly towards the end of the titration. Now we can have selected examples for titrations involving iodine. First of all, we are discussing estimation of iodine. This is the aim of the experiment, to estimate the mass of iodine in the whole of the given solution of iodine. Approximately n by 10, that is 0.1 normal sodium thiosulfate solution and annular potassium dichromate crystals being supplied with. Annular potassium dichromate crystal or K2Cr2O7 crystal is used to prepare a standard solution with which sodium thiosulfate can be standardized. That is, we have to standardize a solution of sodium thiosulfate for which we are using a standard solution of potassium dichromate. The principle of the experiment is described here. In the presence of hydrochloric acid or HCl, potassium dichromate liberate iodine from a solution of Ki. This is familiar to you. In the previous slides, we have discussed this concept. In the presence of hydrochloric acid, potassium dichromate can liberate iodine from a solution of potassium iodide. This is the reaction responsible for that liberation of iodine. K2Cr2O7 plus 6Ka plus 14 molecules of HCl produces 2CrCl3 plus 8KCl plus 7H2 plus 3 molecules of iodine. These liberated iodine can be titrated with Na2H2O3 solution or sodium thiosulfate solution. Iodine oxidizes sodium thiosulfate to sodium tetrathionate as per this reaction. 2 Na2H2O3 plus iodine produces Na2S4O6 plus 2 sodium iodide. This reaction is very, very important as far as the titrations involving iodine is concerned. And since one molecule of Na2H2O3 reacts with one equivalent of iodine, the equivalent mass of Na2H2O3 is same as its molar mass. That is, the molar mass and equivalent mass of sodium thiosulfate are the same. The molar mass of Na2H2O3 5H2O, it should be noted that Na2H2O3 is commercially available as Na2H2O3 5H2O. Its molar mass is 248.19. It is clear that the molar mass is same as equivalent mass. So you can say the molar mass of Na2H2O3 5H2O is same as its equivalent mass, that is equal to 248.19. Now we have to consider about the equivalent mass of iodine in the previous reaction. The equivalent mass of iodine is same as its atomic mass. The atomic mass of iodine is 126.9, that you can take it as 127 for round of calculations. Standardization of sodium thiosulfate solution is used to estimate the given iodine solution. Now, the various steps are consolidated here. Estimation of iodine involves the coming steps. The steps involves preparation of standard potassium dichromate solution, standardization of sodium thiosulfate solution, and estimation of iodine using standardized thiosulfate solution. Now we can discuss another experiment belongs to titration involving iodine. That is nothing but estimation of copper. This is the aim of the experiment, to estimate the amount of copper in the whole of the given solution of copper sulfate, approximately n by 10 sodium thiosulfate solution and Ar potassium dichromate crystals being supplied with. Ar potassium dichromate crystal is used to prepare a standard solution which is used to standardize sodium thiosulfate solution as in the previous experiment. Now, in the presence of hydrochloric acid, potassium dichromate liberate iodine from a solution of Ki. This equation is familiar to you. K2Cr2O7 plus 6Ki plus 14HCl produces 2CrCl3 plus 8KCl plus 7H2 plus 3 molecules of iodine. The equivalent mass is 49, that is the equivalent mass of potassium dichromate, and the liberated iodine is treated with the sodium thiosulfate solution. Iodine oxidizes sodium thiosulfate to sodium tetrathionate as per this equation. This is same as in the previous case. Since one molecule of sodium thiosulfate reacts with one equivalent of iodine the equivalent mass of sodium thiosulfate is the same as its molar mass, and the molar mass of Na2S2O3 is 5H2 that we noted in the previous experiment. It is equal to 248.19. Copper 2 plus can liberate iodine from potassium iodide solution as per this generalized equation. 2Cu2 plus plus 4I minus gives Cu2I2 plus iodine. It is clear that iodine is liberated here. In this reaction, the equivalent mass of copper is its atomic mass, that is 63.54. The liberated iodine in this reaction can be titrated against standardized sodium thiosulfate solution to estimate copper. Now, these are the consolidation of various steps for the estimation of copper. The first step is the preparation of a standard potassium dichromate solution. The second step is the standardization of sodium thiosulfate using potassium dichromate. And the last step is the estimation of copper using standardized sodium thiosulfate or thiosulfate. Now we are discussing equivalent weight calculations. First of all, equivalent weight of an oxidizing agent and a reducing agent. You are familiar with this concept. The equivalent weight of an oxidizing agent or reducing agent is the mass of the substance that it can gain or lose 1 mole of electron during a redox reaction. Equivalent weight is given by the expression molar mass divided by number of electrons transferred per molecule. Number of electrons transferred is equal to total number of electrons gained in the case of oxidizing agent and lost in the case of reducing agent in a balanced redox equation. First of all, we are taking the calculation of equivalent weight of potassium dichromate. Now let us consider the reaction. K2Cr2O7 plus 6Ka plus 14HCl gives 2CrCl3 plus 8KCl plus 7H2 plus 3I2. This is a very popular reaction that we have learned in the reactions, in the titrations involving iodine. Look on this reaction. It is very well clear that the molar mass of potassium dichromate is 294 gram per mole. The number of electrons transferred during the process is 6, and equivalent mass of potassium dichromate equal to 294 divided by 6, that is equal to 49 gram per equivalent. Now consider another reaction. 2Na2S2O3 plus iodine gives Na2S4O6 plus 2 sodium iodide. Here 1 molecule of Na2S2O3 reacts with 1 equivalent of iodine. Thus the equivalent mass of Na2S2O3 is the same as its molar mass. However, Na2S2O3 is available as Na2S2O3 5H2 and its molar mass equal to 248.19, and now we are considering the equivalent weight of iodine. Again consider the reaction. 2Na2S2O3 plus I2 gives Na2S4O6 plus sodium iodide. Here 1 molecule of Na2S2O3 reacts with 1 equivalent of iodine. Thus the equivalent mass of iodine is same as its atomic mass. Equivalent mass of iodine equal to its atomic mass, which is equal to 126.9, that is round off as 127. Now we can have some problems based on the concept we have learned. First of all, how many grams of potassium dichromate are needed to prepare 250 ml 0.5 normal solution? It should be noted that whenever we are discussing about volumetric analysis, calculation of weight required for the preparation of a standard solution is a very popular type of questions. So we have to familiar this kind of problems by doing several examples. This is a similar kind of example, and the question is about the mass of the weight of potassium dichromate required to prepare 250 ml of a 0.5 normal solution. You can calculate the weight required by using the previously studied expression, that is V into E into N divided by 1000, where V represents volume of the solution in ml, N represents normality, and capital E represents equivalent mass of the solute. And you have to substitute the values in respective positions. Volume equal to 250 ml, equivalent weight of potassium dichromate is equal to 49, and you have to prepare a 0.5 normal solution. So numerator equal to 250 into 49 multiplied with the 0.5 divided by 1000 to get a weight of 6.125 gram. That means you have to take 6.125 gram of potassium dichromate and just dissolve it in 250 ml water to get a 0.5 normal solution. Moving on to next problem. Find the weight of Na2S2O3 required to prepare 0.05 normal 250 ml solution. Again, you can use the same expression, weight required equal to VEN divided by 1000. V volume, N represents normality, E represents equivalent weight. Substituting the respective values, we will get the weight required equal to 250 into 248.2 into 0.05 divided by 1000, that is equal to 3.10 gram. That means 3.10 gram of sodium thiosulfate pentahydrate is weighed accurately and transferred it into 250 ml beaker and made up to 250 ml standard flask and made up to 250 ml, you will get a 0.05 normal solution. Moving on to another example. In a titration of standard sodium thiosulfate with iodine solution, the concentration of iodine solution is obtained as 0.05 normal. What is the weight per liter of the iodine solution? It is clear that weight per liter can be calculated by using the expression weight per liter equal to normality into equivalent weight. The normality is given in the problem as 0.51. You have to just multiply with 127, that is 0.51 into 127. The weight per liter equal to 64.77 gram. Now, an MCQ based on the concept we learned. The volume of 0.1 normal sodium thiosulfate required to neutralize 20 ml solution of 0.125 normal iodine solution is. These are the options. Option A 20 ml, option B 25 ml, option C 10 ml, and option D 12.5 ml. You can calculate the volume required by using the expression N1 V1 equal to N2 V2, and whenever you are substituting the values in the simple volumetric equation N1 V1 equal to N2 V2, you will get the right answer as option B, that is equal to 25 ml. This is the last problem. 2.48 gram of sodium thiosulfate 5H2 is dissolved in 100 ml water to get a solution. The normality of the solution will be, these are the options, 0.1 normal, option B 1 normal, option C 0.5 normal, and the last option 4.9 normal. And you can calculate the normality of the solution by using the expression weight per liter divided by equivalent weight. It is possible to calculate the normality, and we will get the final result as option A, that is 0.1 normal. That's all about the present module. Have a nice learning experience. Thank you.